So there is no perfect test in the real world. Okay, that's impossible. That's theory, right? It never occurs. So now let's see what are the limitations of what we have and what can it do. For example, we're talking about our permutation testing, right? In our permutation testing setup, imagine I want to compare these distributions. What we compared in our exercise was the median of xt and the median of xc. We compared the difference between these medians. The median difference is what we compared. We actually did not compare the whole distributions. Our test statistic, was this, which means what we are actually comparing is probably some measure of average value, because this distributions could have outliers. We're talking about some average behavior in the treatment and average behavior in the control. We're only checking for average behavior, not the whole distribution. That is one of the limitations of permutation test. That permutation test still has to be done in the context of a test statistic that we choose. But the advantage here is we can choose any major test statistic of our choice. We can choose mean, we can choose median, we can choose anything that is sensible in our use case, but not the whole distribution itself. To compare whole distributions, we have multiple techniques. One of them is Mann-Whitney-U. Right? We'll just study that in a few minutes. Cool. Again, another very important fundamental assumption underlying permutation testing is that observations are exchangeable. This is very important. So imagine if you have somebody who is in a control versus some user who is in a treatment, right? We can exchange whatever we observed here, right? We can exchange these, right? That's important because by jumbling up everybody, remember, the exchangeability basically says that because we are combining the whole data, and then we are shuffling, and then we are splitting, right? What we are simulating is what if both control and treatment come from the same underlying distribution. By doing this, we are making a fundamental assumption that the data is exchangeable between control and treatment, which is always true if you are using a randomized trial, right? So when you're using randomized trials like A/B tests, this is perfectly all right. Another issue with permutation testing, it's both an issue and a power of it, which is it does not assume any distributions. For example, we had our XC and XC. It does not assume anywhere that XC is Gaussian distributed or this is specifically distributed. It doesn't care. While other tests, right, make some assumptions about it. So the beauty of permutation test is it is completely non-parametric. So again, the whole area of statistics can be broken down into parametric and non-parametric. One of the key points of non-parametric statistics is that it makes no assumptions about the distributions. And it doesn't have any complex assumptions, especially in a randomized controlled trial type of settings. It is super easy to experiment with using simple simulations for a given setup that you have. You can compute your power, which is 1 minus beta, You can compute your power, which is 1 minus beta. You can compute your type 1 and type 2 errors fairly easily, as I just described a while ago. Again, we also have a lot of flexibility with respect to choosing the test statistic. But please also understand that not making any assumptions about distributions is also a weakness. That's something that often is overlooked. Suppose imagine if you have a random variable x. If you tell me that this has a specific distribution, suppose if you tell me that this is normally distributed or Gaussian distributed with some mean and standard deviation, this is additional information. This is extremely powerful. This is additional information given to me. If you don't have it, like for example, if you have this information, because something which is Gaussian or normally distributed has a bunch of phenomenally good properties. I can leverage all those properties to come up with better tests. If you say X, I don't know what distribution it belongs to. I don't know what distribution it belongs to. Then I don't have this additional piece of information. Again, the fact that a random variable belongs to a class of distribution like the normal or Gaussian or exponential or power law is phenomenally useful. So typically, When you don't have any of that knowledge of the distribution, you have less information. Because you have less underlying information or additional information, in the case of permutation testing, you might sometimes need, not always, in the case of permutation testing, you might sometimes need more data. This is the key. So suppose, imagine there is a setup where you can do two tests. One is permutation resampling test. Let's assume there is another test like the T test or the Z test, bunch of other tests. Okay. Suppose all the t-test has some assumptions about the normality of the mean that it's computing and things like that. So imagine if all the assumptions are met, t-test could be able to determine with more power and less errors than your permutation test, because permutation test is not making any assumptions. So in the case of permutation test, you might need more samples than other statistical tests which are parametric. This is true of the whole area of statistics itself. As I was just telling you a while ago, you have parametric statistics and you have non-parametric statistics. The typical dichotomy is non-parametric statistics do not make any assumptions. Because they don't make any assumptions, they might need more data sometimes. Because here in parametric statistics, we are assuming that random variables have some distributions, you might get away with less data because you have additional information about the underlying behavior. Okay, that's very, very important. So never rule out any test. While permutation test is extremely powerful, it is also fairly interesting. Now, okay. So another quick point that I see in the chat window is, why can't we use Chebyshev's inequality? Okay, very nice. So Chebyshev's inequality, for those of you who know it, I'll give a quick answer to this. You can use Chebyshev's inequality. Chebyshev's inequality basically says what percentage of points lie within a specific interval around the mean. That's what it's trying to tell you, irrespective of the underlying distribution. The problem is this is a very weak bound. Okay, this is a very weak bound. This is not a strong bound. Okay, whatever number Chebyshev, because Chebyshev inequality is also not making any assumptions about the underlying distribution except for finite variance and finite standard deviation, if I'm not wrong, right? That's why whatever bounds it gives are very weak as compared to something like z-test. In z-test, you're going to assume that the data is coming from Gaussian distribution. Because you're making that assumption, you can give much stronger bounds. Okay, just quick point. In case you don't know what is Chebyshev's inequality, don't worry about it. Okay, so now comes the other super exciting part. Okay, before we go ahead and learn other techniques, there are many techniques to solve this. We'll try and focus on specifically Mann-Whitney U because it's so widely used. It's also super powerful.